For the past couple days, we've been working on union probability, which involves a very specific type of question. It's kind of like when they say, what's the probability of this or that happening? Then you will use the addition rule. So that's what you've been doing the past couple days, okay? And so remember with that, you just add the probability of one of the events happening plus you add them, you add it to the other, the probability of the other event happening. And then remember that special scenario is if they had something in common, in other words, they're not mutually exclusive, you have to subtract the probability of both of those things happening. Okay, so make sure that you remember with union probability, the OR probability problems, you're adding the probabilities and then subtracting. Okay, what we're working on today is intersection probability, which is a different type of question. Okay, and so with intersection probability, there is a different question, obviously, that you're going to be looking for. So with intersection probability, if you remember when you did intersection and unions with the Venn diagram stuff, they would typically call these the AND problems, and there is a reason for that. Okay, and then remember the intersection problem or the intersection symbol is an upside down U. And so the way that I kind of think about that is intersection. You can think of it, it kind of starts with the sound N. So this kind of looks like, if you think about a lowercase n, it kind of looks like a big lowercase n, okay? And so that's the way I remember the symbol, all right? So the question to look for to know it's one of these types of problems, because it will work differently, is it says, what is the probability of this and that happening? And so what you're looking for is they're going to say, what's the probability of both of these things happening? So that's actually another way that they can phrase it, is if you're wanting both this and something else to happen at the same time, then it's an intersection problem and you actually have to do it differently. Okay, so those are the two questions to look for, is what is the probability of this and that happening, or what is the probability of both of those things happening. Okay, and so the notation that you will be seeing with this is, it'll be like P for probability. So the probability of, and we're going to use the general letter A, of A and B happening. Okay, so that's how you kind of write this in notation, or using the notation. All right, so what this is really saying is what's the probability of A and B happening. Okay, so with that, just like what we did with union problems, there is something you have to figure out before you can actually do the problem. All right, so again, these are very different than how you would do the union problems. The issue is that it's going to feel like it's similar. Okay, and so be very, very careful and try to keep them separated. So if it's a intersection problem, in other words, they're saying, what's the probability of this and that happening? Then what you have to decide first is, are those two things that they're describing independent events or dependent events? So before we actually work on actually solving problems with these, we're going to talk about what the difference in that is, all right? So independent events are events where one event or the outcome of one event actually does not affect the other one. And then dependent events is where one event or outcome of one of the events does affect the other. Okay, and so like an example I can give you is most of you guys may have chores to do around the house. And so, if you have your mom and dad and they say you have to, I don't know, clean or do the dishes before you can go out with your friends, well, that would actually be dependent events, because if you do not do the dishes, okay, the outcome of one event is going to affect the other one, because if you don't do the dishes, then you will not be able to go with your friends. Whereas if you do the dishes, then you get to go out with your friends. So the whether you get to go out with your friends or not depends, there's that word dependent, depends on whether you do the dishes. Okay. And now, if you have really, really like not so strict parents, and whether you do the dishes or not doesn't determine whether you go out with your friends or not, that would be more so independent events. So like if you do the dishes or you don't do the dishes and you still, it does not affect whether you get to go out with your friends or not, then those are independent events. Okay. And so as to which one it is, it's going to affect how you have to do the problem in a minute. Okay. So let's practice before we actually talk about how to do the probability part of it. Let's practice looking at some events and telling if they are independent of each other or dependent. Okay. So look at example number 1. It says independent or dependent events. In part A, it says draw a card from a deck and then you roll a die. So the two events are you're drawing a card from a deck of cards and then you're rolling a die. Are they going to affect each other? Well, if I draw a card out of the deck of cards, is that going to affect when I roll that die and what's going to happen on the die? Well, no, those are kind of two separate things. So these would be independent events. One event is not going to affect what happens when you do the other one. Okay. So then part B, it says you pick a pencil from a box, put it back in. So you're going to draw a pencil from a box and then put it back in. And then you pick a pencil from that same box. Well, this one you might want to consider like the probability and kind of thinking if that's going to be affected. So if I pull a pencil from a box, is that going to affect whenever I pick another pencil from the box? Well, this part right here actually has a big impact on whether they are going to be independent or not. Okay. Or in other words, independent or dependent events. Okay. If let's say that we had 10 pencils in that box, what's the likelihood that I would pull out, like, I don't know, let's say that all the colors of the pencils are different. So all the colors are different. You're picking out, what's the likelihood of pulling out a blue one? And there's just one blue. Well, you'd have a 1 out of 10 chance. Okay, well, let's say we put it back in the box before we pick out another pencil. Well, because we're putting it back in, that means that there's still going to be 10 pencils in the box. So let's say they say, what's the probability of getting a blue pencil again? Well, that probability did not change because there's still 10 pencils and there's still one blue one in there. Okay. And so because we put the pencil back in the box, this event actually does not affect the next time we draw the pencil out. So these would actually be independent. And if that doesn't make a whole lot of sense when we actually do an example in a little bit, you'll see why those are independent. Okay. And so in the next example, you'll notice that there's a minor difference. In this one, it says pick a pencil from a box and don't put it back in. So in other words, you kind of set it to the side and then you pick a pencil from the same box. Well, because we did not put that original pencil back in, that means that there's going to be one less pencil when we pick another pencil. So that will actually affect what happens on this second event. In other words, when we pick another pencil out of the box. So because this other event is affected, these would actually be dependent events. Okay. And then part D, it says you pick a glass from a cupboard that contains 50 glasses and then you break it. I don't know why you're breaking it, but let's say you break it. Then again, you pick a glass. Well, because you are breaking that original glass that you pull out, think about how many glasses will be left over. There's only going to be 49 glasses now. So because of that, that means that when we pick another glass, the likelihood of us getting some certain type of glass will change because there's only going to be 49 glasses left. So that means that these are dependent events as well. Okay, because one, what happens, what we do will affect the next time we do something or the next thing that we're looking at. Okay, the last one, it says you flip a coin 3 times. So you take the coin, you flip it, you look at what you get, you flip it again, and then you flip it again. Are those 3 separate times that you're flipping that going to affect each other? So, like if I flip it once and I get, let's say it lands on heads. Well, if I flip it again, is the fact that I've got heads already going to affect the next time I flip it and what I get? No. And so when I'm flipping a coin 3 times, one flip isn't going to affect what I get the next time I flip it or the next time I flip it after that. So these would actually be independent events. Okay. So, oh, I missed a whole set of letters there. Goodness gracious. Independent. All right. So now that we've practiced telling whether they're independent or dependent, we can talk about what do you do to actually find the probability of certain things happening. Okay, so we're going to come back up here. We're going to plug in our information and then we'll do some examples with those. Okay, so hopefully you will have an understanding when you do the homework. Okay, so what happens if you're looking at the probability of something happening and you find out they're independent? Well, all you have to do if the 2 events are independent is you find the probability of each event and then you multiply those probabilities. Okay, so you multiply the probability of each event occurring. So if they say, what's the probability of A and B happening? You find the probability that A would happen, and then you multiply it times the probability that B would happen. Okay? Now, what happens if they're dependent, though? In other words, one is actually affecting the other. Well, you're still going to multiply the probability of each happening. However, you have to figure out how is that one event affecting the other one. Okay? And so the notation here will be a little bit different, and you'll find that later in this week, you'll find out where this notation comes from. But until we get there, just kind of know that you just have to kind of think through it to figure out how it's being affected. All right. So you're still going to multiply them. So it's the same question. What's the probability of A and B happening? So you still take the probability of A happening, and you're still multiplying it times the probability that B would happen. But this is where the notation gets a little bit different. Okay. So it's the probability that B would happen given that A is true or A has happened, okay? Because remember, this is gonna affect this probability of B happening, all right? Like remember when we broke that glass, there was one less glass whenever we picked out the next glass. So that's what I mean, is you just have to figure out what's changed, okay? So the way that you read this part is you're finding the probability of B happening given that A has happened or is true. Okay. So that's kind of how you read that notation. And this is what's called conditional probability. All right. Which is what we're going to talk about in a couple of days. Okay. So let's practice just going through the whole motion, figuring out is it independent, dependent, and then practicing using the formula for whichever one it is. Okay. So number 2, it says you toss a coin and roll a die. What is the probability of getting heads in an even number? All right. Notice the question here says, what is the probability of getting heads on the coin and then an even number on the die? And it's saying, what's the probability of this and that happening? So if you remember earlier, I said that's kind of the question you're looking for, right? What's the probability of this and that happening? So we know, number 1, it is an intersection problem. And so remember, you have to look at these 2 events and you have to think to yourself, are they independent or dependent? Are they affecting each other or not? So if I'm tossing that coin and I'm rolling a die, are these going to affect each other? Like whatever I get on the coin, is that going to affect what I get on the die? And no, these two don't really have an effect on each other because, you know, what I get on the coin isn't going to determine what I get on the die. Okay. So these would be independent. That's the first thing you have to figure out. Okay. So because they're independent, that's this formula right here. All we have to do is just find the probability of one of them happening and multiply it times the probability of the other one. Okay. So in this problem, we're finding the probability of getting heads on the coin, and getting an even number when we roll the die. Okay, so we have to find the probability that we would get heads times the probability that we would get an even number. Okay, that's what we just figured out because they were independent. All right, so on the coin, what is the likelihood that if I toss that coin, I would get heads? Well, there's one side that has a head on it out of the two, so I have a 1 out of 2 chance there, times the probability of getting an even number. Well, thinking about a die, it has the numbers 1 through 6 on it, right? If it's a standard die. And so there's 2, 4, and 6. Those are all your even numbers. So we have a 3 out of 6 chance of getting an even number, okay? And so from here, I'm probably going to simplify my fractions a little bit before I actually multiply them, because that'll make my multiplying a little bit easier. So I'd have 1/2 times 3 over 6 reduces to 1/2. So it'd be multiply straight across. 1 times 1 is 1, 2 times 2 is 4. So I have a 1 out of 4 chance, or if you change that to a percentage, I'd have a 25% chance of getting a heads on the coin and an even number on the die. Okay, so that's an example of independent events. All right, so let's do some more examples since we have all kinds of different stuff they can ask you about with this. All right. So example number 3 says there are 10 marbles in a bag. 5 of them are blue, 3 are green, and 2 are purple. For part A, it says I take 1 marble out of the bag. I put it back. So in other words, sometimes you'll hear them say that you replace it and then pull out another marble. What is the probability that both marbles are blue? All right. So notice this says, what's the probability that both are blue? Well, that means that the first one that I draw out has to be blue and the second one. So this is an intersection problem. So we're finding the probability of the first one being blue. So I'll just put first blue, and the second one that I draw out is blue. Okay. So before we can do anything, we have to figure out, are these two things independent or dependent? So I'm drawing out a marble, I'm putting it back, and then I'm pulling out another one. So does that change anything whenever I go to draw out the second one? And this is kind of like that example I talked about before. Because I'm putting it back, that second marble that I draw out, the likelihood of it being blue will not change in any way. And you're going to see why, okay? And so because of that, because the second marble I draw out not being really affected, these would be independent events, okay? So with that, I just have to take the probability of the first one being blue, and I have to multiply it times the probability that the second one is blue. Okay, so let's kind of do a little calculation here. So the probability that the first one is blue, well, if we look up here, 5 of them are blue, and then there's a total of 10 marbles in all. So the probability of the first one being blue, we have a 5 out of 10 chance. All right, times the probability that the second one is blue. Well, if you remember, and this is why this part's so important, we put the first one back before we drew out the second marble. So because of that, that means that there's going to be the same number of marbles in that bag. And so that's why these are independent, is because nothing has changed really with how many marbles there are in all, and how many blue ones there would be and all that, okay? So the probability of the second one being blue, well, there would still be 5 blue ones out of the 10 total. And then again, you can simplify, or you could just type that in all at once. But I like to simplify a little bit. So 5 out of 10 is 1/2. So it'd be like 1/2 times 1/2. And that would equal 1/4. So that one's just coincidence, but we got the same answer as the other one. So we have a 1 out of 4 chance or a 25% chance of both of them being blue. All right. So let's look at the next example. It says, I take one marble out of the bag, put it to the side. In other words, there's no replacement there, so I did not put it back. And then I pull out another marble. What is the probability that both the marbles are blue? So notice it's the same question, probability that both of them are blue, but this is going to change the numbers, all right? So this part will actually be exactly the same as what we had, okay? And so I'm just going to go off of that. So we're still finding the probability that the first one's blue and the second one's blue. But this part will change just a little bit, and you're going to find out it's because of this part right here. Because we are not putting the first one back, that means that there's going to be one less blue one in the pack. So that means these are dependent, because that second probability, that second marble that we draw out will be affected because we didn't put it back, okay? So for the notation here, we're finding the probability that the first one is blue, and we're still multiplying because it's still an intersection, but we have to multiply it times the second one, or the probability that the second one is blue, given that, well, the thing that changed it in this first event is that we did not replace or put the marble back. So I'll just put did not replace the marble that we drew out. Okay, so that's why this one's being affected. All right, so you'll notice, and it won't really be a hard problem to figure out, it just changes how you do it. All right, so the probability that the first one is blue, well, there's 5 of them out of the 10, so that won't change much. But now that we didn't put the marble back, there's one less blue marble and there's one less marble overall. So we have 4 out of 9 chance now that second one will be blue. Okay, so that's the part that's being kind of affected. All right, so then from there, just like before, you just type it in your calculator, and because the 5 out of 10 will reduce, but the 4 out of 9 won't. And so you could just type it in. And have calculator figure it out. So it'd be 2 out of 9. And then that would be roughly 22.22% chance that both of them would be blue. So notice that is different. So this little part right here does change things. So pay attention to that. All right. Part C, it says, I take one marble out of the bag. I put it back. In other words, I replace it. And then I'll pull out another marble. So notice this is kind of back in place. I've put the marble back. It says, what is the probability I pull out a green marble and then a purple marble? All right. So this one's just changing what we're trying to get out. So we're finding the probability, and it's an intersection because it says what's the probability of getting this and that. So we're finding the probability that the first one is green and the second one is purple. Okay, so are these being affected? Or are these events independent or dependent? Well, kind of looking up here, we took a marble out, we put it back, and then we pulled out another one. Because we put it back, that means that these aren't going to change numbers because we're not changing how many marbles there are in the bag. And so these would be independent events, so we don't really have to concern ourselves with how does something change, okay? So really all we have to do is find the probability that the first one's green times the probability that the second one is purple, okay? So we just have to look at what's going on in the situation. So what's the probability that the first one that we draw is green? Well, we got a 3 out of 10 chance because there's 3 green marbles in the bag out of the 10 times the probability that the next one's purple. Now, remember, we put the first one back. So the thing that would change if we did not put the first one back is there would be, like, we're assuming that the first one would be green, right? That just means that there would be one less overall, okay? Because the second one, we're wanting to be purple, all right? So, but just kind of talking about what would be the other case if we didn't put it back, okay? But we did put it back. So we just have to figure out what is the probability that the second one's purple. Well, there's 2 purple ones out of the 10, okay? There'd still be 10 in there. So we'd have a 2 out of 10 chance that the second one's purple, okay? So from there, we just have to type it in, or we can reduce and simplify. Either way. From there, as a fraction, we get 3 out of 50. So we have a 3 out of 50 chance of getting a green and a purple one, or that is 6% chance as a percentage. So we have a 6% chance of getting a green and then a purple one out. All right, so the last couple of problems that we're going to do are just different types of problems that you may see with the intersection stuff. And they're actually a little easier than the problems we were just doing, but you just have to know how to approach them. All right, so number 4 says, if something is shown to be 95% effective and you use it once a week for an entire year, what is the probability that it will work every time the entire year? Okay, so what this is meaning when it says something is 95% effective, okay, that means, because a lot of advertisements use this and a lot of people do not understand this. So make sure that you understand how this works. When something is 95% effective, that means that if you use that, whatever that is, 100 times, 95 of those times it will work, but 5 of those times it won't work, okay? Or just based on probability. Remember, probability is an approximation, all right? So it's not definitely going to be a thing, right? But it's just based on the data that they've observed, okay? And so if something's 95% effective, that's what's going on, okay? Out of every 100 times you use it, it'll work about 95 of those times and won't work about 5 of those times, okay? And so we're given a scenario here. Let's say that you use it once a week for an entire year, and you're trying to figure out what is the likelihood, what's the probability that it'll work every single time that whole year that you're using it, okay? Well, this is actually an intersection problem because you may not realize it, but they're asking you really what's the probability that it works the first week and the second week and the third week that you use it, and the 4th week and the 5th week, so on and so forth, for the entire year. Well, one thing you have to know for this problem is how many weeks are there in a year, because you're using it once a week for an entire year, right? So, well, one thing you have to realize is that there are 52 weeks in a year, okay? So that's the first thing. And the reason why these problems are a little easier than the other ones is because they actually give you the likelihood of it working when you use it once. That's what this is telling you, is the likelihood that it works, period, is 95% chance. So the likelihood that it works that first week is a 95% chance. The likelihood that you use that it works the next week, I'm assuming you're using like a new product every week or whatever. The likelihood it works the next week is a 95% chance that it's going to work. 95% chance the third week it's going to work, so on and so forth, okay? So what is the likelihood that it works every week that entire year? Well, it's an intersection problem. So all you have to do is take the likelihood it works each week and multiply them, okay? So we just discussed the likelihood it works the first week is 0.95. The likelihood it works the next week, and I just change it to a decimal, 0.95, and then you keep going for the entire 52 weeks. So a quicker way of doing that, instead of taking this times itself 52 times, is, remember, you can just bring that number to the power of 52, or however many times you want to multiply it times itself. So if I type that in and I take 0.95 to the 52 power, 52nd power, I get 0.0694 if I round it there. So that means, because that's the decimal, if I change that to a percentage, it would be 6.94%. So the likelihood that that product will work that entire year is 6.94%. So remember, now this is a very specific percentage, but that's not a good likelihood. But the reason why that's so low is because, remember, like I said a second ago, out of the 100 times that you use it, it should fail, according to the percentage, about 5 times. So you are about to use it 52 times in a row, right? And you're asking yourself, what's the likelihood it's going to work all of those times? Well, this is the likelihood that it would work every single time that you use it for that entire year. Okay. So just something interesting to see. All right. So we'll do one more. Hand sanitizer usually says that it's 99.99% effective at killing germs. Okay. So it says if you decide to use this once every day for a year, what is the likelihood it would work at killing the germs every time that you use it for the entire year? Okay, now remember, this isn't just cleaning your hands the whole day because you have to reapply, but let's say that you just use it once a day for a year. Well, this is kind of like that other question, except this time you're using it every day, not every week, but every day. So think about how many days are in a year. There's 365 days. So the likelihood it worked the first day you use it is 99.99%. The second day, same thing, so on and so forth. So if you're finding the probability or the likelihood that it would kill the germs each time that you use it for that entire year, you would change that to a decimal. So it'd be 0.9999. And you're using it every day. So that would be 365 times in that year. And so you multiply that times itself 365 times. So that's a quicker way of doing that would be bring it to the 365th power. And that ends up being 0.9642. So that as a percentage would be 96.42%. So the likelihood it worked that entire year, every time, each time you use it, would be 96.42% chance that it worked that whole year at killing the germs when you use it. All right. So let me know if you have questions. Have a wonderful day.